Valentin Christiaens, who will be presenting on VIP, a package for high contrast imaging.
Hi, everyone. Can you guys hear me?
Yep, we can hear you, and we can see your screen.
All right, perfect. So hi, my name is Valentin Christiaens. I'm a postdoc at the University of Liège, and it's my pleasure today to present to you the Vortex Image Processing Package, or VIP. So this project was initiated in 2015 by former PhD student Carlos Gomez, and I've been the maintainer and lead developer for a few years now. So we benefited from inputs from a large number of contributors. So I first want to address my warmest thanks to all of them, if some of them are listening. So our initial goal was to integrate state-of-the-art high contrast image processing algorithms and make them available to the community. So the main mottos we try to follow was to make our resource open source, try to have efficient implementations of different algorithms. We wanted them to be easy to use, so beginner friendly, and for that we also included tutorials on how to use the package. And we also wanted it to be well documented. So there've been 2 publications to date presenting the package. So there's been a Journal of Open Source Software paper that was just accepted last month, which summarizes basically all the new additions and new features that have been added to the package since our 2017 paper. So I picked a random color, say purple, to highlight new features throughout this talk. So pay attention to purple in the next few slides. So the package depends on a number of open source of Python open source packages. We didn't want to reinvent the wheel, and so we really wanted to be part of this open source community. So there's been a range of science cases on which VIP has been used. The most prominent one and the initial motivation of the package is, of course, the detection, so the direct imaging and characterization of substellar companions. We've also used it to image protoplanets or protoplanetary disks. It's also been used to image and forward model debris disks. It's also been used to study high mass star formation, since this is also a high contrast issue. We typically have an early type star surrounded by a lot of stellar mass companions. So the package has also been used as a base to develop ever more advanced exoplanet detection algorithms, be it based on neural networks or on a combination of state-of-the-art algorithms that are implemented in VIP. So VIP follows a modular architecture. The first and largest module is the one containing all the algorithms for that can be used to model and subtract the stellar PSF, and so to go from a sequence of raw chronographic images to post-processed images that can reveal substellar companions or extended disk features. Another important module is the pre-processing module, which contains different operations that can be applied to your data before the PSF modeling and subtraction. So we can go through this in a second. Another module is the one gathering different sorts of metrics, such as the signal-to-noise ratio map that can help you evaluate the significance of the signals you detect in your post-processed image. It also contains implementation of contrast curves or variants of it, completeness curves, which can give you an estimate of the achieved contrast as a function of radial separation from your star. So we also have a forward modeling module that can help you characterize any detected point source or extended source. And we also have a new module that includes inverse problem-based algorithms, such as Andromeda or Paco, or algorithms based on match filtering. So And on top of these 5 main modules, there are also some support modules containing lower-level routines or wrappers or functions already implemented in other major Python packages, which routines of the 5 major modules can depend upon. So I won't have the time to cover the whole package in just 10 minutes. So we'll just focus on some cherry-picked recent additions to the package. So let's start with pre-processing. So as I said, it implements a number of routines that can be helpful to prepare your data before PSF modeling and subtraction. So we have different routines for star recentering, but automatic bad frame rejection, bad pixel correction, or PCA-based sky subtraction. And we also recently implemented basic image operations, such as subpixel shift, scaling, and rotation, using a Fourier transform based approach, which, as I'll show here, is much better at preserving the signal in your data, which can be crucial for achieving a high contrast. So in the test I'm showing here, so I took an original image and I scaled it 18 times with different scaling factors, and then descaled 18 times with the inverse scaling factors, and I showed the results on the left column and the residuals with respect to the original image on the right column. First, for a typical interpolation kernel-based approach, so the lungs of 4 kernel in OpenCV, and second, with our new Fourier transform-based approach. We also implemented that for rotation, image rotation, which is used widely in high contrast imaging. And again, I compared the results obtained with different kernels and our new Fourier transform-based method. And as you can see, the results are pretty much null after so 72 rotations of 5 degrees of the original image. And yes, we can see it's performing much better. Another module, as I mentioned, is the PSF modeling and subtraction module. So we have a range of different algorithms already implemented. I won't have the time to go through all of them, but I can give you the broad idea that is followed by these different algorithms. So all of them leverage angular differential imaging. So you typically have as input an image sequence obtained in pupil stabilized mode. So pupil stabilization enables you to have a relatively static stellar halo over time, while you have your field of view that rotates. So any hidden planet in your data would rotate with the field of view. So you can leverage that information to make a model of your stellar halo and subtract it. You end up with residual images, which you then align, you derotate them, and finally stack them to have a post-processed image. And the main difference, so all these algorithms follow this pattern, and the main difference is on how you actually calculate this stellar halo model. So we've had this for a while, but recently we've added the possibility to combine angular differential imaging with spectral differential imaging. So spectral differential imaging can be applied on integrograph and spectrograph data. So in IFS data, you acquire images at different wavelengths simultaneously. So you can use that information as well to build a stellar halo model. As is shown here, you can see that a typical airy ring would expand with wavelength, while the position of a planet would not. We can leverage that information as well to build an even better stellar halo model for subtraction. We can see here at work where the square here shows the area where the stellar halo model was subtracted. So a recent module we've added is the one with inverse problem-based algorithm. Again, I won't have the time to go through all of them, so I'll just take the example of Andromeda. So in Andromeda, we have first a pairwise subtraction of frames taken close in time, and with the angular differential imaging strategy. With this pairwise subtraction, you expect most of the stellar halo to be subtracted, and any true companion would have a positive, negative signature as shown here. And you can then calculate at each location in your field the likelihood for the presence of a companion with a given amplitude. So you can look for the maximum likelihood to find the amplitudes, and you can get a detection signal ratio map and the photometry of any putative companion at each location in your field. So we also have the forward modeling module, which helps you to characterize any detected planet or disk. So in this module, we have routines to inject synthetic planets, to inject synthetic spirals or disk models in your data cube. We also have a new module to create scattered light disk models. And we also have the negative phase companion technique implemented there. So let me just focus on this new module, the scattered light disk that allows to build scattered light disk models. So this class takes as input some disk geometry, some user-defined dust density and distribution, and a choice for a scattering phase function. And from there, you can use the compute scattered light routine, and it will output an image that corresponds to the chosen geometry, in this case, a very inclined disk, and with a distribution corresponding to a thin ring. And from there, you can apply different post-processing algorithms to do forward modeling and see what kind of geometric biases you end up with, and you can compare that to your observations. And I see I'm running out of time, so I wanted to just briefly mention, but I won't go into the details, the fact that VIP was used to implement the Exoplanet Imaging Data Challenge, the two different phases of it. So the first phase was about finding out what was the best planet detection algorithm. So it was Easter egg hunts. We injected different planets in different data sets, and each participant had to find those planets. And we computed the score to evaluate all the 22 algorithms that were submitted. And at this stage, we are in the phase 2 of the challenge, which is still open. So I take advantage of this talk to encourage you to participate. So in this phase, we want to evaluate what's the best algorithm to extract the position and the flux of directly imaged planets. And in this case, we have 8 data sets that are obtained with integrography and spectrographs, with 21 injected planets. We have a website, a Zenodo, that contains those data sets. We implemented a GitHub that provides some resources such as tutorials how to perform this, and we have a platform on where to submit the results. I'm running out of time. I'm just going to leave you with this colorful summary that used to air as targeted advertisement at previous conferences. There you go. Good. Thank you for your attention.
Excellent. Thank you so much for that wonderful talk. Was incredibly thorough. This is incredible. Do we have briefly any questions? Let me. I really have more of a clarifying question for anyone that is interested in participating in phase 2. I saw that it is until June of 2023. So is that like through June as well, you can participate in this challenge?
Yeah, it's until the 30th of June at 11:55 p.m. European time.
Perfect. Okay. Yeah, just wanted to make sure it's not June 1st.
No, it's the end of June. Yeah.
Fantastic. Well, thank you so much, Valentin, again, for a wonderful talk.
No worries.
And as always, people can ask further questions or keep the discussion going in the Discuss Talks Slack in the thread for this talk.